Hello everyone, welcome to a video for Algebra 2A. We're on week 2 going through linear inequalities and functions. Alright, so week 2 assignments, make sure you watch this video, look over our CK12 textbook, and you have 2 assignments for this week, the paper pencil problems and our weekly test. So objectives for this week. If I give you a relationship between two variables, either in points, a table, or a graph, I want you to be able to determine if it's a function or not. Would you be able to analyze a function either in graph form, table form, equation form, and determine what the domain and range are? If I give you a point, can you determine if it's a solution to a linear inequality, either by using the graph or by using the algebra symbolically? I want you to understand the relationship between a graph and the symbolic representation of that graph of a linear inequality. And then if I give you a series of data, can you determine a line of best fit that models the data? That's what we're going to be working on. Obviously, it's a lot. A lot of this is still kind of review, but again, I want it to be fresh in your head. We're really setting the stage for functions this whole year. All right, so what is a function, right? That's a lot of our theme for this week. What is a function? If you remember, we can express relationships between two variables a lot of different ways. We can express it as an ordered pair. For example, 3, 5. That point means when x is 3, y is 5. I can make a table of values, right? We can make our x and our y values, make a little table, pick some points, 6, 9, 12, and we can represent a relationship between our two variables that way. We can make a graph. So we've done a lot of graphing where we can see what is happening between our x values and our y values graphically. Again, the graph represents all the possible points and relationships between x and y. And finally, we have a lot of equations. Last week, we reviewed a lot about linear equations and linear growth. These are all different ways to show a relationship between our two variables, x and y. If I change x, the independent variable, what happens? What do I get back from my output value y? Okay, so in math, as we're working with all these relationships, points, graphs, tables, we love to distinguish in these relationships when we have a function. So functions are this big idea, and all a function is in math is for every relationship, if there's an input variable x, and for each x, there is only one, that's the big idea, there's only one possible output variable y, then we call that relation a function. We give it a special name. We're going to look at a lot of different examples of relationships between two variables that we would actually classify as functions. That's the big idea. You want to write that definition down. For every input variable x, there's only one output variable y. Okay, let's take a look at the following sets of points. We've got two sets here, 3, -2, -4, -5, 7, -2, 9, 1. So there's 5 points. And this other set of 5 points, 4 points. Maybe not be an idiot here. 4 points and 4 points. One is a function and one is not. How can we determine which relation is a function? Well, we go with the idea of each input variable has only one. So here we go, let's take a look. Here, x, if I input x, it turns into a y value of -2. So 3 turns into -2. Here, x is -4, turns into a y value of -5. This x value of 7 turns into a y value of -2, and this x value of y turns into x value of 9 turns into a y value of 1. Each x value is unique, 3, -4, 7, 9, and they only turn into one y value. So this one is the function. Every x value turns into only one y value. All right, let's contrast that now with the other one. All right, -4, this x value turns into a y value of 1. 0 turns into 3. 0 also turns into 0, and 6 turns into -7. Did you catch the difference there? Here, 0 is turning into two different y values. Either I put 0 in to get a y value of 3, or I put 0 in to get a y value of 2. That is two different output values for the same x input value. So this is not a function. It's a relation. I can plot these points. I can represent them. There's something mathematical going on, but it is not a function. All right. Let's take a look at a kind of more of a table format. Which one is a function, which one's not? Well, again, each input value has to have only one output value. So 1 turns into 5, 2 turns into negative 1, but look what we got here. 3, this input value turns into two different output values. So this one is not a function. If I input 3, I get 6. Or I get 7. That's two different outputs. However, look at over here. 5 goes into 1, negative 1 goes into 2, 6 goes into 3, 7 goes into 2. Now, some people may be a little bit weirded out and saying, well, look, there's two inputs that give the same output. And that's okay. A function is a one-way thing. Each input has to turn into only one possible value. And if I put in 7, according to this, I get back 2. That's the only thing I get back for 7. If I input negative 1, I only get back 2. That's the only output. So this is a function. All right, let's take a look at two graphs. Two graphs. Which one is a function and which one is not? All right, on this first one, let's see what's happening here. Let's take an x value of 1. There's actually two different points for that x value, right? It looks like if x is 1, I get a y value of 2.8. But if x is negative 1, if x is 1, I also get a y value of negative 2.8. That's two different y values for the same x input value. So that is not a function. And it actually brings up this idea of the vertical line test that you're reading about. If I have any graph, I can draw a vertical line, and if it crosses more than once, it's not a function. Contrast with this other one. It's kind of an interesting function. It's actually a trigonometric function, but if I draw my vertical lines, each x value has only one y value. So this is a function. All right, so once we've defined a relationship to be a function, we then like to be able to describe key characteristics of the function. One of them is domain and range. Those are kind of big ideas when we work with a function. A domain, when we talk about domain, it's all of the x values, is not just one. It's all of the x values that we can put into a function that actually give you an output. Range, on the other hand, is all of the possible y values. So now we're getting y values, thinking about our two variables here. All the y values that we can get back as we input values into the function. So let's look at some examples of domain and range. All right, here's some points. 1, 2, 3, 4, 5 points. Is it a function? Is it not a function? Well, looking at it, I've got an x value of 9, 7, 4, negative 10, negative 2. They're only defined over those x values. So it is a function, yes. There's no repeating x values to get different y values. Yes, it is a function. Now, what is the domain and range? Well, the domain is all the possible x values. So let's go say domain. Which x values work for this function? Well, it looks like I got 9, 7, 4, negative 10, and 2. Let's write them in order. So negative 10 is the x value. That gives me an output. Negative 2, 4, 7, and 9. For those 5 points, those are the x values that I'm specifically given that actually work in this function. I don't know about any other x values. I'm not given that information. So there's the domain, those five x values. The range is all the possible y values. So what do I get back? My y values are 2, -3, -6, 4, and -7. So the range would be, let's go -7. That's a value I get back, -6, -3, 4, and 2. All right, there's my domain and range for this particular function defined by these 5 points. Let's look at another one. Here I've got a graph going on. What's happening here? So graphically, the arrow is indicating right here that this graph is going on infinitely this way. And the arrow here is indicating it's going on infinitely that way. There are no gaps or breaks in my graph. It's what we would call continuous. And so what we would define is I can look and say, okay, wow, for all my x values, if I pick any x value, I can find a point on my graph for that x value. Just picking some here. If I pick an x value of 8, there's a point. If I pick an x value of -6, there's a point. And in fact, with the arrows on the ends, it looks like all x values, I can find any point on this graph and find an x value. So my domain for this linear function, domain is all x values. I'll write it a bunch of different ways. All x values, there's no limit. Or another way to say it is x equals all real numbers. There's kind of a fancy way of writing an R for all real numbers. So x can be anything. X can be any value. There's no limitation. The same thing with a range. If I look at my y values now, I can pick 4. There's a point on the graph where I have a y value of 4. If I pick 1, there's a point on the graph where y equals 1. And any y value, I can go along and find the graph and a point on that graph that has that y value. So the range is also all y values. There are no limit to what y values I get back. So y is also equal to r for all real numbers as well too. So sometimes we have functions with very clear limits on domain and range. Sometimes we have functions where anything is in the domain and range. All right, here's a good example of domain and range where we'll have a function with specific limits. So let's see what we got going on here. So my function, there's this point right here. It stands out. I'm going to take a note of that. That's an x value of -2 and a y value of -3. And from the left of that, all these x values work. The arrow then means it goes infinitely and infinitely. However, there's a gap from -3. There's no place on my graph in this little section. It starts back up right here and then goes to the right. So all these x values work. But as I write my domain, I need to recognize this little gap, this break. So that point right there with the open circle is an x value of -1 and a y value of +1. So what is the domain? All x values such that x has to be less than or equal to -2, right? So from -2 onward, it's a solid point, so it includes -2. And or, that's a or, x is greater than -1. Not equal to, because it's an open circle. It's not filled in, so it doesn't work at that point. So the domain, this function only works if x is a value less than or equal to -2, or it's greater than -1. If it's in between -2 and -1, this little gap right here, it's undefined. That is not in the domain. All right, how about the range? So now my range, remember, is all the y values. So let's take a look at my y values. So if I look at this, I can find a y value for any point. I can find a section on my graph, but there is sort of a value where it won't get below. The range in this one, notice my graph never goes below a y value of -3. So my range is all y values greater than or equal to -3. Those are the only places on my graph where this thing will work. So between these x values, with these two inequalities, and between these y values, I can never have a point on this graph with a y value less than -3. Okay, hopefully that helps you understand domain and range in a few different examples there. Again, with functions, we're going to be working with a lot of different functions in this class this year. We've already been touching on linear functions. We'll review quadratic functions, but the new ones will be polynomial functions, digging more into exponential and logarithmic functions, radical functions, rational functions, and trigonometric functions. And for each function, we're going to look at how does its graph work, what are characteristics, including domain and range, what makes that function unique from other functions, and we'll be using the functions to model situations and solve a variety of problems. All right, functions, functions, functions. All right, switching gears. Let's do a little bit of inequalities. A linear inequality is simply any linear equation. So we got x and y. It's a linear, so it'll form a line. It's got two variables. However, instead of an equal sign, we have an inequality symbol. So for example, we've got y is less than or equal to 3x minus 5, or we got 2x plus 5y is greater than 21. Let's play around a little bit with inequalities. Since these are inequalities, there's an infinite number of ordered pairs that satisfy the inequality. We're not looking for one solution, we're looking for all the possible solutions. So let's find some in here. I need y values that are less than or equal to 3 times x minus 5. Well, one solution could be -5. If I put -5 in for y, and if I put 1 in, whoa, let me get that backwards. If I put -5 in for y and 1 in for x, let's see what happens here. So -5, is that less than or equal to 3 times 1 minus 5? Well, yeah, -5 is less than or equal to -2. So that's true. There's one solution. Well, if that y value is less than it, well then let's find some more. That means 1, -6 is a solution. Means 1, -7 is a solution. These are all y values that are going to be less than -2. You can see really quickly we can find an infinite number of solutions. There's 4 just like that, and I've only picked one x value to work with. What if we have a big point? Is the point 135 a solution? Well, again, all that's saying is if we put in 100 for x and 35 for y, is this inequality true? So let's check it out. Is 35 less than or equal to 3 times 100 minus 5? Well, 3 times 100 is 300, minus 5 is 295. And yeah, I would say 35 is less than or equal to 295. So yes, it is a solution. There we go. We've testing points. We're kind of understanding what this inequality is trying to show us. All right, so lots of solutions. Is there a nice way to represent all the solutions? Yes, if we use a graph, we can graph all the solutions to the inequality. So here we go. If you want to graph all the solutions, get your linear inequality into slope-intercept form, graph the equation of the line to get the boundary. In our boundary line, we're going to determine from the inequality if it's solid or dotted. And then we're going to determine when it's in slope-intercept form if we shade up for all the solutions or down for all the solutions. And we can use a test point to double check your graph. Let's kind of go over that here. Here's my inequality. I want to graph all the solutions. First thing I need to do, let's get it in a slope-intercept form. So I'm going to move 2x to the other side by subtracting it. So now I've got 5y is greater than -2x plus 21. I'm going to divide both sides by 5. And we've got y is greater than negative 2/5 x plus 21/5. And 21/5, 5 goes in 21 4 times, so that's the same as 4 1/5. All right, let me make a really fast graph now. There's my y-axis. My x-axis, I have a y-intercept of 4 1/5. So let's go 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So there's positive 7. It's my x-axis, positive 7. Negative 7 on the y-axis. 1, 2, 3, 4, 5, 6, 7. Okay, let me switch to a different color. So now that it's in slope-intercept form, my y-intercept is 4 1/5. So I can plot a point right about there. My slope is negative 2/5, so it's going over 5 down 2. So let's draw that. 1, 2, 3, 4, 5. There's over 5, down 2. And before I draw the line, again, I'm kind of graphing it like I would the equation. The boundary line, this is a greater than symbol, which means y is greater than, but it's not equal to at that point. If it was a line under for greater than or equal to, I would draw a solid line. But since it's greater than, I have to draw a dotted line to show that, yeah, this inequality doesn't actually include the line. The line is just a boundary to help me understand the inequality. So there you go. There's my boundary line using my slope and my y-intercept. But now I want to shade all the y values greater than that line. So here's where all the solutions are in this area above the line. This is shading it in. And this is all the solutions. Everything in this point, all of these points, are solutions to the inequality. There's an infinite number of them, right? And now let's pick a test point. Let's pick, let's see, 1, 2, 3. Let's pick this point 3, 6. It's in the shaded area, so if I put in a value of 6 for y, is that greater than negative 2/5 times 3, an x value of 3, plus 4 1/5? All right, so let's use my calculator here. Negative 2/5 is the same as 0.4. Right, so we got 0.4 times 3, so that's negative 1.2, plus 4 1/5 is the same as 4.2. Negative 1.2 plus 4.2 is 3. And is 6 greater than 3? Yes, that's true. So we just tested it out, and I'm feeling pretty good about my inequality. Any point in this shaded area is going to be a solution to this inequality here. We just graphed the whole solution set. Now, that was doing it by hand. We can actually use the Desmos calculator to do it as well. It's really handy. So we're going to take the same inequality, and I'm going to show you how to do that. All right, here I am in the Desmos calculator. Let's put in the inequality we had. It was 2x plus 5y is greater than 21. 2x plus 5y. There's my inequalities down here on the keyboard, so we're going to greater than 21. And look at what we got. We have the same dotted line. There's my same y-intercept at 0 at 4.2 that we had. And here's all the solutions, this whole shaded area right here. So again, the Desmos calculator is a handy way to be able to quickly represent solution sets and to work with inequalities as well. All right, our last topic for this week is reviewing how to find a linear equation to a set of data to model a problem. And we've been working with linear functions, linear inequalities, and all a line of fit is if I'm given a set of data in two variables, data all around us, right? Lots of data, scientific data, taking observations. We like to look for patterns in the data. We like to mathematize it, right? Or take that data and see, is it have an equation, a pattern that it fits. So we can use the equation that we create to then make predictions, understand what's going on, make decisions, and use our data to be smart. So here we go. We have some data from music sales from 1999 to 2009. So over these 10 years, what is the pattern? Here's some data sales, right? Looks like we sold a lot of music, but it's starting to kind of decline. Then it picked up over these 3 years, but then it's starting to decline again. Can we make a mathematical equation, a line of fit that seems to model what is happening? All right, so let's talk about how to do that. The first thing is, if I'm trying to make a linear equation, let's eyeball a line of fit. We want to take a ruler and try and draw a line as best as we can that seems to follow the pattern of our data. Usually you want the same number of points above, same number of points below, but there we go. It may be a little bit different. Again, freehanding it is a little bit tough, but we've got a good set of data. So now I've got a line. I need an equation for this line. And you know what? I think I'm going to actually draw a better line. Notice no points are actually on this line, right? So, and I could also draw this trend line. Let's do switch colors and let's make a blue one go more like this. So it's not quite as much of a slope, but I can now use this point and I can use this point to help me come up with an equation that seems to fit that data. So if you're doing it by hand, obviously there's going to be some variability, and that's starting to lead into statistics in terms of you can use a model to get the exact line of fit and have methods to know how well does your line fit. And there is one line that will fit that data better than others, but if we're doing this by hand and eyeballing it, it's okay to have a little bit of variability. We're again just trying to find the pattern. So looking at this, I would say we're going to use the point in 1999. And let's actually use the full 1999. Then let's call it about 15 billion in sales. And then our other point is in 2008. Let's go 9 billion in sales. So those 2 points are on my line of fit. And once I got 2 points, that's enough to make an equation. The slope is going to be, subtract your y values. So 15 minus 9 is going to be negative 6. 1999 from 2008, if I subtract those, that's going to be 9. And what do we have? We have over a 9-year period, we lost $6 billion. Or I can reduce it down and my slope is negative 2/3. About every 3 years, the music sales declined by $2 billion. That's what our slope means. All right, now we can use a point to write an equation. So I'm going to use point slope form. Y minus y1 equals m times x minus x1. That's the easiest way if we know a point and a slope. My slope is negative 2/3. And I'm going to use this point right here, 2008 and 9. So x minus 2008 equals y minus 9. And there is a linear equation based off the slope of the 2 points and based off one of the points we were given, that if I graph that, it's going to go through the data and it's going to model the data. And now that we have an equation, we can put in x values, we can solve for y values, we could extend it in the years 2010, 2011, 2012. We can do a lot of stuff with this mathematical model. That's coming up with a line of fit that fits data. So again, to recap, to do a line of fit, you want to get the data, graph it, draw a line that best fits the data, pick 2 points close to the line, use those 2 points to find the slope, And then once you have the slope and the 2 points, you can write an equation in either slope-intercept form or point-slope form, whatever you're most comfortable with. And then you'll have an equation that models that data. All right, week 2 is done. Good video. So what do? We did a lot of graphing with points, tables, graphs, determining if it's a function or not. We analyzed the function to determine domain and range of a lot of different examples. We did some linear inequalities, determining if a point is a solution and being able to graph all the solutions. And then finally, if you have a series of data, we can find a line of fit that models the data. Lots of stuff with reviewing and understanding and working with linear equations and functions. Have fun working on your assignments for this week.